All right, section 3.2, the product and quotient rules. Now, back in the previous section, we mentioned a sum and difference rule that we could use for finding the derivative of a function, which essentially allowed us to differentiate the function term by term. And that rule said that the derivative of a sum is equal to the sum of the derivatives, right? And equivalently, the derivative of a difference is equal to the difference of the derivatives, right? But we said essentially that just allowed us to differentiate term by term. But I also mentioned at that point that there was no product or quotient rule that worked the same way. In other words, the derivative of a product is not equivalent to the product of the derivatives, and likewise with quotients. So here's a quick example just to show you why that's the case. So I'm looking at this function f of x equals x times x squared, which of course could be written as x cubed. So let's take it in the form of x cubed, and if you differentiate x cubed using our power rule, we get f prime of x equals 3x squared. Now we know that's a correct derivative because that's the power rule that we used in the previous section. So let's instead try to differentiate this by simply taking f of x equals x times x squared, and let's see if the product of the derivatives is the same as the derivative of that product. So I take the derivative of x times the derivative of x squared, right? So just taking it straight as a product. The derivative of x is 1, the derivative of x squared is 2x, but 1 times 2x gives me 2x, which is not the same as 3x squared. Now again, we know this to be correct because that was basic power rule. That's the derivative of x cubed, which is 3x squared. If we do it just by using the product, I get something different over here. So that tells me right there, this is not a correct process because I get something completely different from what I got on the left. All right, and again, we know the one on the left is correct. All right, so there's one simple example, and if it doesn't work for one, then I can't trust it for any other one. So the derivative of a product is not equal to the product of the derivatives. Now that's generally speaking. Of course, you could run into individual cases where maybe that's true. But generally speaking, for any type of function, that is not a correct statement. So then we have a product rule, a process that we follow for finding the derivative of a function. And, going forward, and as I talked about at the beginning of the previous section, there's two things that we're concerned about when we're differentiating a function. And we said the first is what type of function you're working with, function or functions, because we're going to be working now with multiple functions. And the second is there a process involved in the differentiation of the function? Okay. So this product rule, I call that a process, right? The product rule is in play regardless of what type of function you are differentiating. Right? Different types of functions have different processes for finding their derivatives, as we will continue to talk about. But then we also have these other processes that are used in conjunction with these different types of functions. So the product rule is one of those processes. And what the product rule says is that if I have two differentiable functions, f and g, then the derivative of their product, f times g, is equal to the first function, f, times the derivative of the second function, so we'll call it g prime, plus the second function, g, times the derivative of the first function, call it f prime. And of course, there's different notations that can be used for all this stuff, but I think the easiest way to remember the product rule is to differentiate the product of two functions. I take the first times the derivative of the second plus the second times the derivative of the first. All right, and again, different people have different ways of stating this and different ways of remembering it, but I think that I find that to be the most straightforward way for a product rule. So first d second plus second d first. So for example, take the function f of x equal to the product of the square root of x times e to the x. All right, so again, first thing I have to recognize is that I am looking at a product, and this becomes more and more difficult as we address more and more scenarios. Like I tell you at the beginning of section 3.1, if you take an individual function of a specific type, we're going to have a process for finding its derivative. But once you start combining multiple functions and multiple processes, obviously the process gets a little more difficult. So you have to recognize, the different types of functions that you're working with. You also have to recognize the different processes as they appear. So when I look at this function f of x, yes, I see the square root function. Yes, I see an exponential function base e, but the overlaying process here is that there's a product of those two functions. And so automatically, product rule. So I'm taking then f prime of x, and I have this written out in detail, and I'll mention something when I finish all this, but here's f prime. Now, like I said, make sure you're labeling everything clearly. Once you start the differentiation process, then go ahead and label that as f prime. So our product rule says to take the first function, which is square root of x, times the derivative of the second function, plus the second function times the derivative of the first. Now, I'm writing this out in detail so that we're clear on exactly what's happening. At some point, I would expect that you wouldn't necessarily have to write this step, that you could probably go straight to finding the derivative of each one of these in the course of differentiating that function. But for now, I'm being very detailed so that we're clear on exactly what's going on, and then as you become more comfortable with the processes, you can consolidate some steps. But that's all just a matter of personal preference. If you prefer to write it out in detail every time, then do that if you find it helpful and useful to do it. My main thing with all of this is don't try to do too much in one step. I find that to be probably the biggest issue with differentiating functions where there's a combination of different functions and processes. It's trying to do too much in one step, right? So take it a step at a time. If you find that you're having problems with it, maybe I'm trying to combine too many steps into one, break it down into smaller steps. It's all about getting it correct. It's not how fast you get it done. It's not how many lines you write. I have to write things that are correct. So if you need to break it down into smaller steps, break it down into smaller steps. There's nothing wrong with that until you become more comfortable with it. So there's our product. So I have the first times the derivative of the second plus second times the derivative of the first. Now, once you write that out, now that takes care of the product rule. That's the process. Now we can just focus on, let's find each of these derivatives that we're asked to find. Okay? So that's maybe kind of an advantage to writing it out this way. You write out the general rule, and then you go back into your statement and say, okay, what do I actually then have to differentiate? And so I need to find the derivative of e to the x. I need to find the derivative of square root of x. Now, next step, I went ahead and wrote that square root using exponential form. We did that back in the previous section so that we could use our product rule, our power rule, excuse me. So what I did for the derivative of x to the 1/2, all right, try that again. Derivative of the square root of x. I went ahead and wrote that as x to the 1/2, so I could differentiate using our power rule, which would be 1/2 times x to the negative 1/2. And then I went ahead and rewrote that back into radical form, because I think square root of x is a pretty basic function that we're going to run across on a pretty regular basis. So maybe just knowing what the derivative of that is without having to go through all of this is going to save you some time. So let's commit this to memory. Let's take square root of x, which is one of our basic functions, and I'll say that the derivative of the square root of x is 1 over 2 square roots of x. Right? And so that saves us the time of having to go through the whole power rule process. But again, if you're not comfortable with it, fine. If you don't remember, fine. Run it through the power rule process and you can get your derivative. All right, otherwise, e to the x, that's our most friendly function, right? Remember, the derivative of e to the x is e to the x. So here's our square root of x times the derivative of e to the x, which is e to the x, plus e to the x times the derivative of square root of x, which we just found to be 1 over 2 square roots of x. Now, what you're going to find to become a bigger and bigger issue is maybe not so much the derivative. That's going to require enough work in its own. But once you find the derivative, we then need to rewrite our function into a presentable format. I think I mentioned a little bit about that in the previous section. That's going to become certainly more and more of an issue as we get into more and more complex functions. So you don't want to leave it looking like that. You want to try to clean it up a little bit, make it look a little bit more presentable. But as I mentioned before, without the simplification becoming the main focus, and then two, there you still have options as far as how you eventually choose to write the function. So I would at least take this, and as I have it written, I rewrote it as e to the x times square root of x plus e to the x over 2 square roots of x, and write it that way. Quite often you will see factoring done. I can tell you, especially in the solutions manual, they love to factor. So factoring out that common factor of e to the x, which leaves us with square root of x plus 1 over 2 square roots of x, and writing it that way is also acceptable. But I would at least ask that you would write it, cleaned up just a little bit. Whether or not you put it in factored form, that's not as big of an issue. That's just personal preference. So I mentioned to you before, and I said this is half the battle sometimes. It's to recognize that what you have and what you see as the solution are actually the same. Maybe they're just written differently. So when you do these derivatives, or when you find these derivatives, and you check your answer, if what you have and what the book has is different, don't automatically assume that what you have is incorrect. You may have it correct, you just may have it written in the different forms. So can you take what you have and make it look like what the book has? Or vice versa. Can you take what they have and make it look like what you have? Right? Can you see that the two are equivalent? So that's sometimes an issue, and there's no way around that. You just have to recognize these different forms. A lot of it is just basic algebra stuff, like we've mentioned before, rewriting things algebraically different. Okay. So there's a lot of suggestions that I'm giving you here in addition to the actual process, but that's how the product rule works. It's regardless of what type of function you have, right? You set up the process and then you differentiate each piece as according to the process. The second one I have, f of x equals the product of 2x cubed plus 3 times x to the fourth minus 2x. And you notice it says show both ways. There's two different ways that you could do this. And I mentioned again before, and certainly again as we get into more complex functions, sometimes you do have a choice as far as how you proceed in finding the derivative. It may be a matter of how you choose to write the original function, or it may be a matter of which process you choose to use in the actual differentiation. So sometimes you have choices. There's no right or wrong way to do it. I mean, if I can do it two different ways, both ways are perfectly acceptable. The difference is usually there's going to be a more efficient way. Right? There's going to be a process or a method that is quicker than doing it another way. So we try to find the most efficient, quickest way to do it. But bottom line, as long as we get it done, that's the main thing. So if you end up taking a little more scenic route and you get to the final result, as long as that's correct, then we're good. So I'm never going to dock you or take points away from you for doing it a different way. Right? I'm just going to say find the derivative of the function, and if there's different ways that can be done, as long as you get it done correctly, that's fine. Right? So if you can see the more efficient way, then certainly we're going to go that route. So I'm going to do this from two different ways. So notice this is just the product of two binomials. So it is a product, right? So I did it using product rule, where our first function would be the 2x cubed plus 3. The second is the x to the fourth minus 2x. So there's f prime using product rule. There's our first times the derivative of the second plus the second times the derivative of the first. And then I went in and found each of these derivatives that we are asked to find. Right? So again, you write out the product rule, and then you go back and actually differentiate each of the individual functions. So there's 2x cubed plus 3. There's our derivative of x to the fourth minus 2x, which is 4x cubed minus 2, those basic power function. Plus, we've got x to the fourth minus 2x times that derivative of 2x cubed plus 3. The derivative of 2x cubed would be 6x squared. The derivative of 3, remember, the derivative of a constant is 0. So again, notice I'm only differentiating where it says differentiate. That's why I'm always a stickler about writing proper notation. There should be no interpretation on what's written. You do what it says. And if you follow what you have written, there should never be a question about what should be done. You do what it says to do. Now, I'm actually finished with the differentiation, right? There's no more derivatives to be found. Now it's all about rewriting the function. So certainly, I've got a product up here in the front. I've got a product in the back. I mean, this is not a factored form of that polynomial, so what I chose to do in this case was go ahead and multiply all this stuff out. So I used the FOIL method up in the front, and I've got the 8x to the 6 plus 8x cubed minus 6. If I FOIL those two binomials, and then on the back end I distributed the 6x squared to get the 6x to the 6 minus 12x cubed. And then we just combined like terms, and I end up with my derivative, 14x to the 6 minus 4x cubed minus 6. So we could call this f prime. That is my derivative. Now, so there's another way that you could do this, and because the original function is nothing more than the product of two binomials, let's just multiply them out first, right? So instead of differentiating first, I chose to first FOIL those two binomials, and if you multiply those out, you get this. You get f of x equals 2x to the 7th minus x to the 4th minus 6x. So that's just rewriting the function. And then we differentiate the function. Well, that's a heck of a lot simpler because now I'm just differentiating that power function, or at least those terms that are each power functions. So there's our derivative of 2x to the 7th, 14x to the 6th. There's our derivative of x to the 4th, 4x cubed, and our derivative of 6x, which is 6, which notice is the same thing that we got over here. So that's what I mean by, you may be able to take the function, and depending upon how you choose to write the function, you don't always have to take it in the form that it's written. If I can write it into a different form that allows me to differentiate much more simply or efficiently, then why torture yourself, right? But of course you have to recognize that. So here's two different ways. I got the same result. Either way is fine. This one's just a little more of a scenic route. This last example on this page is really just kind of playing again with the product rule, and showing us how we can manipulate that thing. So it just helps to remember and how to manipulate a product of a function when you're finding its derivative. So I'm taking this function f of x, which is the product of the square root of x times some function g of x, which I don't even know what g of x is. So it's the product of square root of x times g of x. We are given the fact, though, that g of 4 equals 2 and g prime of 4 equals 3. So we're given values for g of 4 and g prime of 4. And then we're asked to find the value for f prime of 4. All right. So I'm starting with the function f of x equals square root of x times g of x. If I want to find the value of f prime of 4, I think it makes sense to first find f prime of x. So that's what I did. So here's our function. I said, okay, I want to evaluate the derivative. Let's find the derivative. Well, there's a product. It's the product of square root of x and g of x. So I'm following product rule. First times the derivative of the second, derivative of g would be g prime, plus the second times the derivative of the first, which is square root of x. And then again, you go in and find any derivative that you can find. In this case, since I don't know what g of x is, I certainly don't know what g prime of x is. So I'm just going to leave that as square root of x times g prime of x. I don't know any more than that. But I do know the derivative of square root of x, because that's the one we found in the previous problem. So then this becomes g of x times that derivative of square root of x, which we found to be 1 over 2 square roots of x. Now that's f prime. That's at least an equation for it. So then let's find f prime of 4. Well, how do you find f prime of 4? Well, you plug 4 into f prime. So I'm just plugging 4 into our derivative. Square root of x is now square root of 4. G prime of x is now g prime of 4. G of x is g of 4. And 1 over 2 square roots of x is 1 over 2 square roots of 4. Square root of 4 we know to be 2. G prime of 4, that's where we come back up to the original problem, and we are given that value. We are given that g prime of 4 equals 3. So I went ahead and plugged that in place of g prime of 4. We then hit g of 4, which again in the problem we're told that g of 4 equals 2. So I just went ahead and plugged that in place of g of 4. And then simplifying 1 over 2 square roots of 4, the square root of 4 is 2. 2 times 2 is 4, so I get 1/4. And then I just did the calculations from there. Right? So 2 times 3 is 6. 2 times 1/4 would give us 1/2, and then 6 plus 1/2, 6 1/2, or 13 halves. Okay. So that's just another little example of where we're just playing with the product rule. Right? Doesn't matter what the function is. Product rule works the same for all functions. Quotient rule. So just like the products, there is no direct quotient rule like there is a sum and difference rule. So in other words, the derivative of a quotient is not equal to the quotient of the derivatives. So there is a much more involved process. The quotient rule is a little bit more complicated, and I always say with any of these functions that you're differentiating, the quotient rule is kind of your method of last resort. All right? In other words, if I have a function that's written in the form of a fraction, if I can rewrite that function into a different form or a simpler form, I try to do that first. Now, of course, sometimes that's not possible and you're stuck with a fraction no matter what you do. So then you have to fall back upon this quotient rule. All right? So two issues with the quotient rule. First of all, the rule says that if I have the derivative of a quotient, so the derivative of the quotient of f and g, that is equal to the denominator g times the derivative of the numerator f prime minus the numerator f prime times the derivative of the denominator g prime, all over the square of the denominator. An easy way to remember this one, you think of this in terms of finding the derivative of a high function over a low function. And then we can sing like the seven dwarfs. That is equal to low d high minus high d low over low squared. So I take the low function times the derivative of the high function minus the high function times the derivative of the low function over the low function squared. So obviously, like we said, this quotient rule is a bit more complicated. Right? There's a lot more to it. Secondly, I guess the two things that I always see mistakes made with the quotient rule. First is with the subtraction. Maybe I should say three things. So the product rule, remember there was a sum there. It was first d second plus second d first. Quotient rule is low d high minus high d low. So that's the first mistake I see made. The second is getting these two pieces backwards. All right. So low d high minus high d low, or whatever works to help you remember that. F over g. I've got gf prime minus fg prime. And then the third thing is forgetting the denominator has to be squared again. All right, so over low squared. So there's three parts, I guess, to that. The three typical things where I see mistakes made. So it's like any other formula, you do what you have to do to remember that formula. So let's take, for example, then the first one I have is f of x equals x cubed plus x over x to the fourth minus 2. Let's find f prime of x. So like I said, sometimes there is no choice. That's a fraction. There's nothing I can do to simplify that. You could try factoring. You could try maybe breaking it up. But again, there's nothing that can be done there. So there's a no choice here in terms of the process that I have to use. So here's f prime. Now here's f. X cubed plus x over x to the fourth minus 2. So let's write out f prime. And just like I did with the product rule, write it out in detail first and then go back and find each of the individual derivatives. So here's our low d high minus high d low, all over low squared. And then you go back in and you find each of the derivatives as indicated. So here's our x to the fourth minus 2 times the derivative of x cubed plus x, which is 3x squared plus 1. Minus, there's the x cubed plus x times the derivative of x to the fourth minus 2, which is just 4x cubed. Again, remember our derivative of 2, derivative of a constant, is 0. And then all of that is over x to the fourth minus 2 squared. Now again, we're done with the derivative. That's the derivative of our function. That's f prime. The rest of it is all about putting f prime into a more presentable format. Right? Like I said, it's probably not the derivative that's going to cause most of your issues with these, provided you know the processes. It's going to be the rewriting of that derivative once you're done. And again, I keep saying these same things, but I know these are common issues that come up with these. The question is, well, what can I do to rewrite it, or what should I do to rewrite it? Which form do I want to put it in? That kind of thing. So my rule of thumb is we always try to simplify as much as possible. You know, basic multiplying, combining like terms, simplifying, that kind of thing, without making the simplification process more burdensome than it is. Right? So I mean, this, I'm looking at that numerator. I'm multiplying everything out. I'm using FOIL method with those first two binomials here. And then I'm distributing the 4x cubed in the second times x cubed plus x. But now this is all back to basic algebra, folks. And I've said this before. It's the basic algebra that's going to cause more of your problems than anything else. You've got to remember basic algebra when it comes to simplifying expressions, working with fractions, that kind of thing. And then we're fixing to get into trig functions. And you've got to remember your basic trig identities, your basic trig function values, those types of things. And any of that you have to go back and review, then that's your responsibility. You're going to have to, I presume that you can work basic algebra and basic trig. So that's all we're doing from this point forward. So I multiplied all this out. I used the FOIL method at the beginning, minus, and then I distributed the 4x cubed. And then I went ahead and distributed that negative through that second parentheses. And notice my denominator, I just left it as x to the fourth minus 2 squared. I didn't do anything with this. I always say leave those in factored form, because you may end up having some simplification that can be done once you finish simplifying that numerator. But you know, so I don't want to multiply all that stuff out and then turn around and have to factor it. So leave it in factored form if it's in factored form, and then check to see if you can simplify it. So then once we multiplied everything out, I combined a few like terms up there, and I ended up with f prime of x written in this form: negative 1x to the 6th minus 3x to the 4th minus 6x squared minus 2, all over x to the 4th minus 2 squared. And just looking at that numerator, especially with that negative coefficient on x to the 6th, I don't think there's anything that we'll be able to do to factor that or simplify it. So this, at least, is a lot more presentable than the original derivative that we had, which was here once we finished all the differentiation. Okay, so yeah, I mean, those are the issues, and I know, I mean, there's a lot of things that you have to keep track of, but that's the nature of the beast. That's how these work. Now, if you think that's ugly, let's look at the next one. And again, I'm going to do this one in two different ways. So I've got this function g of t equal to t minus the square root of t over the cube root of t. And again, notice I say there that I can do it two different ways. Excuse me. So this time I'm going to do it the easiest way first. And this is always a recommendation, because like I tell you, if you can bypass quotient rule, we do everything we can to bypass quotient rule, because obviously, like we said, even with just this one, it can be a little bit messy, you know, not necessarily difficult, it's just messy. So if I take this function g of t, and just remind you again some basic algebra, remember you can always take a fraction that has a multi-term numerator, and you can break that fraction and rewrite it with each term over your denominator. So this function g of t can be rewritten as t over the cube root of t minus the square root of t over the cube root of t. Now the next thing I'm doing is just simplifying. So I first then rewrote those in terms of exponents so that we could use our properties of exponents to simplify. So that cube root of t becomes t to the 1/3. That square root of t becomes t to the 1/2. And then I simplify. Rule of exponents says what? Subtract exponents. So for the first one, it's 1 minus 1/3, which would be leave me with t to the 2/3. And then the second one, I'm subtracting exponents, 1/2 minus 1/3. There's some basic fraction calculations, so that would be 3/6 minus 2/6, leaves me with 1/6. Now all of this is rewriting g of t. Notice I haven't done anything to find a derivative yet. All I've done up to this point was taken that original function and written it into a different form. And the advantage here now is, look, now I'm just dealing with basic power function, power rule. So I can find the derivative of t to the 2/3, multiply by 2/3 and decrease by 1, subtract 1 from 2/3, and I've got negative 1/3. So I've got 2/3 t to the negative 1/3 minus, and again, multiply by the exponent and then decrease by 1, so 1/6 minus 1 leaves me negative 5/6, and there's our derivative. And that's pretty straightforward. I mean, yeah, we could talk about then rewriting it with positive exponents or radicals and all of that, but not necessary. I mean, now that we're getting into more complex functions, at least if we can find the derivative and at least try to simplify it by combining like terms, multiplying things out, that type of thing, that's usually sufficient. But, again, you could write that in a lot of different ways just depending on what you want to do. Now, here's the alternative. So I went ahead and started back with the original function, t minus square root of t over cube root of t. And so, okay, let's try to do this using that quotient rule just to show you what happens here. So quotient rule says low d high minus high d low over low squared. So here's our low d high minus high d low over low squared. And so again, first thing I did was rewrote the radicals in terms of exponents to use rules of exponents to make the differentiation and simplification easier. So there's t to the 1/3 derivative. I wrote the square root of t as t to the 1/2. All right, so all I did was just rewrite that previous step by converting the radicals to exponents. Radical form to exponential form. Now we're going to go in and find each of those derivatives. So there's our t to the 1/3. Here's the derivative of t, which is 1, minus the derivative of t to the 1/2, which, I'm just playing with the exponents here, so I'm not bothered with the radical part. 1/2 t to the negative 1/2. Minus, that big minus sitting in the middle right there. T minus t to the 1/2 times the derivative of t to the 1/3, which is 1/3 t to the negative 2/3. I multiply by 1/3, subtract 1. And the denominator, notice all I did was, that's just rule of exponents. There's no derivative down there. Right? You only do a derivative where you have the derivative written. So that's t to the 1/3 squared. Remember, power to a power, we multiply. And so 1/3 times 2 gives me 2/3. Well, let me mention something else here too, because I haven't really made this a big issue in these different, or with these different functions that I'm working with. Notice when I write the dd notation, I'm using the variable within the function. So if my variable is x, I use ddx, like we did up here. If my variable is t, then I'm writing d dt. Because remember, it's always, what are you differentiating? I'm differentiating that function with respect to what variable. Okay. And I know magically things always turn into x because that's our most common variable, but you do want to keep track of your variable. All right, so then each of those derivatives is done, and once I'm done there, differentiation is finished. The rest of it is all simplification, but notice this is an ugly function. I've got all this exponential stuff, I've got fraction stuff, and all that. So, I went ahead and simplified this thing to actually show you that you do end up with the same thing that we got above. But again, it's just still basic algebra. I multiplied out, I distributed the t to the 1/3 through here. You get this. I distributed the 1/3 t to the negative 2/3 through here to get this. I also accounted for the negative that has to be distributed as well. So that's where this came from. And my denominator remained the same. Then I had a couple of like terms that I could combine. So I combined the like terms, the 2 t to the 1/3 and the 2 t to the negative 1/6 to get that. Then I went ahead and split them up. So there's the breaking up of the fraction. And then I simplified. And, I eventually ended up with the same thing. I'm not going to be so concerned about this. I did eventually end up with the same thing that I got up here. But again, notice it was a much more scenic route as opposed to what we did right here. So that's why I say again, if you can take a function that is written in the form of a quotient and you can write it into a different format, or a format that allows me to use a different process, That's typically going to be preferable to trying to use the quotient rule. Okay? Now, of course, there's nothing wrong with using the quotient rule. It's just usually the more complicated process given a choice. Okay? Last little example. This goes back to a question we've dealt with before. It says to find the equation of the tan line to the curve y equals e to the x over x at the point whose coordinates are 1, e. Notice if you plug 1 into that function, you get e to the first over 1, which is e. So I want the equation of the tan line. So that goes back to, one of the things that started all this discussion about the derivative. If I want the equation of a tan line, I first have to know its slope. And that's what the derivative is, right? So I take our function, y equals e to the x over x. Now that's written as a quotient. I'm going to use quotient rule. I'm also going to show you another way to do this. You do actually have an option here. But I'm going to use quotient rule. It's actually not too bad because the functions are not very complex. So here's our quotient rule. I'm finding the derivative. Why do I find the derivative? Because that is what I use to find the slope of my line, my tangent line. So here's y prime, which is low d high minus high d low. Now notice I didn't write anything else there. What's the derivative of the denominator? The derivative of x is 1. So that's our first d second, low d high minus high d low. Let me not confuse that with product rule, which happens all the time, like I told you. So that's low d high minus high d low over low squared. And then since we're specifically using this to find the derivative or the slope of the tan line at a specific point, you don't even necessarily have to bother with simplification there. You can plug in the value that you want. We said find the slope of the tan line at the point 1e, so I'm going to go ahead and plug 1 into my derivative, and that'll give us 1 times e to the first minus e to the first over 1 squared, which e minus e is 0. And this is just touching base again with something we've seen before, and I tell you this is going to be a reoccurring theme for us. Remember, that's the slope of our tan line. What if the slope of the line is 0? What does that tell me? It tells me that the tan line is horizontal. And if the line is horizontal, what does the equation of a horizontal line look like? It's y equal to some number, which would have to be the y coordinate of the point that the line passes through, right? So if I've got the point 1e on my horizontal line, then the equation of that line would have to be y equals e, whatever that y coordinate is. Now I told you there was a second way to do this derivative. This one's not too bad, because like I said, the function is not too complex. But here's another way that you can do it. Some people prefer to do it this way, because like I said, you can avoid quotient rule by rewriting e to the x over x as e to the x times x to the negative 1. Right? Using the rule of exponents. And then you're using product rule. Right? So it's just all a matter of how you choose to write the function. So I can write it this way and then use product rule to find my derivative. So there's our first d second. So the first is e to the x, derivative of x to the negative 1 would be negative x to the negative 2. Right? Multiply by the exponent, decrease by 1. Plus the second times the derivative of the first, which the derivative of e to the x is e to the x. So there's our derivative, and then I just rewrote it as negative e to the x over x squared plus e to the x over x. And I did this just to show you that I did get the same thing. And then I'm going to add those two fractions. Well, remember, basic algebra, if you're adding fractions, what do you have to have? A common denominator. So I'll need to multiply that second fraction by x to give me x squared in the denominator. First fraction is fine. And then I can combine those two. Now notice I've just reversed them because the second one is positive, first one is negative. So I've got x e to the x minus e to the x all over x squared. And that's what we got when we did it the first time, right here. Okay. So I just wanted to mention that because I do see people do that. There's nothing wrong with it. It's just a matter of preference. But again, it just depends on how complicated the function is, how much mess there is there that you're going to have to keep track of. So with a fairly basic one, You can kind of get by doing this, and it's not too bad. But in this case, I think just using quotient rule is actually the better choice because you don't have to worry about the negative exponents and all of that. But it's still personal preference. Okay? But either way gets you to the same result. All right, so that's product and quotient rules. Like I said, the biggest issue I have with those is just making sure you know the rules, obviously, and don't get the wires crossed between them. All right? Product rule has addition, quotient rule has subtraction, and then you have to watch the order of the combination of the function and the derivatives. That is section 3.2.